The next type of problem you might see is you're given some information about a quadrilateral, and you have to say, is it always, sometimes, or never a parallelogram? So if we read the directions, it says, consider quadrilateral ABCD with diagonals that meet at E. Given the following information, can you assume the quadrilateral is always, sometimes, or never a parallelogram? Well, for all of these, I'm going to start with a diagram. It just has to be some sort of quadrilateral labeled ABCD. And for number 1, I'm given that angle A is congruent to angle C, and that side AB is parallel to side CD. So, the first question I'm going to ask myself is, can this be a parallelogram? And yeah, absolutely, it can be a parallelogram. So my answer is not going to be never. It's going to be either always or sometimes. So now we have to ask ourselves, must it be a parallelogram? All right, well, let's think through this. And what we know is if that the left and the right sides, if AB and CD are parallel to one another, think about what's the relationship between angle A and angle D? Well, if you said that they're going to be supplementary, you'd be right. They're consecutive interior angles. When we trace them, they make that C shape or that U shape. And so therefore we know that they're going to be supplementary when the lines are parallel. We can say the same thing about angle B and angle C. They're going to be supplementary. So what we have here is now I want you to consider angle B and angle D. And do you see how they are supplementary to two angles that we know to be congruent? B and D are supplementary to C and A. So because they're supplementary to two congruent angles, what does that tell us about angle B and angle D? Well, it tells us that they have to be congruent to one another. They must be congruent to one another because, do you remember that congruent supplements theorem? If two angles are congruent to two, no, I got that backwards. If two angles are supplementary to two congruent angles, then the angles are congruent to one another. So that tells us that angle B is congruent to angle D. And then look at that. We have two sets of opposite angles that are congruent to one another. So this always is always a parallelogram because it's got two sets of congruent opposite angles. So let's move on to number 2. So I would recommend that you start the same way. Draw it up. And mark it. And the first question I'm going to ask myself is, can this be a parallelogram? And yes, it can be. So my answer is not going to be never. So what you might be thinking is, well, is there any way that I can kind of use the information given to prove more stuff? Well, we know that C and D, for example, are going to be supplementary. We know that the same thing about B and A, they're going to be supplementary. But really, that's about it. We can't prove that any angles are going to be congruent. We can't prove much. So this is going to be a sometimes. If you're not seeing this, I'm going to suggest a counterexample. So I'm going to suggest a counterexample, meaning an example that shows that this is not always true. I'm going to draw what's called an isosceles trapezoid. Isosceles trapezoid has two sets of sides that are parallel and two sets of sides that are congruent. But it's definitely not a parallelogram. So although this could be a parallelogram, it doesn't have to be. My suggestion is right now that you press pause and you try 3, 4, and 5 on your own. Try to model them out, and then I'll show you the answers. Okay, so here's our answers. Number 3 is never, and I think that this is a pretty obvious one. Although T is the midpoint of BD, T is not going to be the midpoint of AC, because I know if AT is 6 and AC is 11, that means TC has to be 5. So this can never be a parallelogram because the diagonals do not bisect each other. With number 4, 4 is a tricky one because you might look at this and you might say, well, looking at this, I know that this triangle, triangle ABD, is going to be congruent to this triangle. I know those two triangles are congruent. I can prove that by side, side, side. Well, that's fine and good, but it really doesn't show us anything else. We can't really show that opposite sides are parallel or anything like that. So this is going to be a sometimes. And again, we could have that same counterexample, that isosceles trapezoid counterexample. Isosceles, that's a really bad isosceles trapezoid. Let me fix it. Isosceles trapezoids, they're going to have, for example, the left and the right side parallel. They're also going to have congruent diagonals. But once again, they're not parallelograms. Number 5 is an interesting one. Knowing that the AB and CD are congruent, the way I drew it, the left and the right side are congruent, and knowing that we have a set of congruent angles, well, what that tells us is that these two angles, angle CAB and angle ACD, they're alternate interior angles. If they're congruent, I know that the lines that form them are going to be parallel. So I know that AB and CD are going to be parallel. So I know that I have two sides, one set of opposite sides, that are both parallel and congruent. So that shows that this is always a parallelogram.